Hello class. So today I will continue on chapter 2. Before doing that, I would like to make sure you guys know for week 2 what we're gonna do by firstly click on the course material. Let me actually change to be a student view. Um, let's see. Okay, now you're gonna click on the course materials and then click on the week number 2 here. You will see that I have paused two things. One is about download chapter 2 over here. Okay, I also will post the recorded video 2.1 and recorded video 2.2 later on. Also, after that, you will go to website.net to finish section 2.1 and 2.2 before January 30. After you finish all this, you will go to Google number 2 over here. In Google number 2, you will have to submit all the file in PDF. Okay, don't submit in any kind of other file, any other kind of file, because it's hard for me to see what it is. So whenever you submit it by PDF, I can see it easily, and you can combine all the files in one by click on this link, which is combinepdf.com. And you're going to follow through this step. The first one, you will have to take notes and submit all the notes you have taken from 1.1 to 1.5 and then 2.1 and 2.2. Actually, the note from chapter 1 and the note from 2.1 and 2.2 today. Then after that, you will finish and submit your session of the Google number 2 over here. You will either to download it or see it. You can click on that, and then you're gonna see and you can download the Google number 2. To go on that. So and then you submit it here by click the launch over here, so you can submit it in the discussion board. And then you're gonna reply to at least 2 other students you think about your thinking. And this Google 2 is due by 11:59 p.m. 2.1 February 1st. Okay, so let me start to work on chapter 2 today. Okay, all right, so okay, let me see, where is my pen? Okay, so in chapter 2 we're going to talk about limits and derivatives. So we investigate limit and their properties, the special type of limit that is used to find tangents and velocities give rise to the central ideal in differential calculus, which is a derivative. Okay, so let's talk about section 2.1, the tangent and velocity problems. Okay, so in here, suppose I have a particle P move along a line. So let's say P was at 0 here. So here's P, right? And at like initially at t equals 0. Okay, I have P over there, right? Then P move to from 0 to 2. Okay, so P to here, and then like I say, like after t equal to say 1 second, right? And then it keep moving and move to 5, right? After 1 more second, which is t equal to 2. So this can be represented by a function, and let y equal to ft be the position of particle at time t. So I will have the graph of this function will be, you should know that's like this part gonna be 0 0, right? So this is like uh, t, and then the first one is t, and the second one is value of p. So the second one gonna be 1 and then 2, and then the third one will be 2 and 5, right? So I have the first part was 1 over here, second one was 1 2 over here, and the last one is 2 5 over here, right? So I will just connect it, right? Connect it. Okay, not really good. Let me try one more time. Okay, and then I connect the next one. Okay, this one is not straight line, right? It is like it is different slope. See that? So yep. So and then it may keep going up, right? We know that it's just the position will keep going farther and farther for P, right? So the definition of the velocity is how fast the particle is moving in the positive or negative direction. So remember that's where the velocity is just how fast, right? And it's moving in the positive or negative direction. Okay, so do you think, the question is, do you think the particle move faster in between time 0 to 1 seconds or 1 to 2 seconds? If you see, uh, if you see from 0, let me use other color. So from 0 to 1 is here, right? If you see the one from 0 to 1, uh, and then maybe use a green one, and then from 1 to 2 over here, oops, right? Then you can see that now the one that's from 1 to 2 make the position go faster, right? You so then I can say the one from 1 to 2 have more distance, travel. Okay. Let me see. All right. Now, question: how do we measure velocity? Okay, so the answer is it depends. Okay, so another definition: we say a particle is in motion. Uniform motion. If it has a constant velocity, so if the velocity doesn't change, then we have uniform motion. Okay, so for uniform motion, you have seen in maybe in physics, right? It could be you would see the form as distance will be equal to the rate, I mean the velocities multiplied by time. Okay, in mathematics we can call it distance equal to the rate multiplied by time, and then we notate by d equal to r multiplied by t, or in the if we divide by t both hand side, we're gonna have r will be equal to d over t, right? So velocity will be equal to distance divided by time. Okay, remember that's just only for uniform motion. Okay, now example 1. Suppose a car is going on a straight line at 20 miles per hour. Let's model it. Okay, so uh, so start from here, right? Here is let here's y-axis and here's x-axis, and the y-axis is stand for the distance. Okay, and the x-axis stand for actually I'm gonna say time, right? Time, t or t. Okay, so let's start from here as time at the initial point, time equals 0, and if suppose the car is going on the straight line at 20 miles per hour, so we just gonna like have a straight line like this, right? And then we're gonna have like a, let's say from here to here. Okay, we're gonna try to figure out we call like from this point to this point, what is the difference, what is change in time? Is delta t. Okay, delta t or delta x, sorry, I gotta say delta x in here. Yep. Because we label it is x. Delta x over this one gonna be distance, right? So it is a change in time, a change in distance. The x gonna be change in time. Okay, so change in distance is say delta y. So usually we're gonna have like the slope will be the rate will be d over t, right? Distance change in distance over change in time, which equal to delta of y divided by delta x. In the previous math, we could call it as a slope. So I'm gonna say here is slope, or in here we call like the rate velocity. Um, so we have like d over r equal to, sorry, d over t, distance over time, will be equal to r as the velocity. Velocity. Right. So we can say velocity equal to slope. Velocity from physics can be measured by slope in mathematics, right? So what if the particle speeds up or slow down? Okay, so I have a graph of the particles over here, and you see that um, the more the faster the faster particle go up over here, it actually means the speed up, right? So we could choose another like we can choose 2 points to calculate the average velocity, right? So let's say I'm going to choose point A is here. Oops. A and point B. Point B, we have the value is B here, right? Then we're going to try to find the average velocity from A to B over here, right? Yeah, in order to find the average speed, right? From this spot to this spot. So I'm gonna have draw a line, go through these 2 points. This is called secant line because it's go through 2 points of the curve. Okay, so we call secant line, and in order to find the average velocity, you actually gonna find the slope of the secant line. Okay, so in order to find the average velocity of the curve, you actually gonna find the slope of the line. Let me use other colors for you to see it's clear. Okay, so we could choose another point, or we could choose, say we could choose we could choose 2 points and calculate the average velocity, average velocity on the interval A, comma B. Okay, so we have average velocity will be, let me try to average velocity from A to B will be equal to the change in the position, right? Change the distance. I'm gonna say a change in position. Change in position. Change in position. So position was here P, and over the chain in time. So T here, right? Okay, so that's gonna be equal to what? You need to know, you know that this point over here, it have the coordinate was A and Y of A, right? F of A. I can say F, let's say YA, right? Y, the Y value in the case that x equal to A, right? So for this one, this was YA. And then for the other point, is will be, you coordinate it. Let me see. Should be around here. Okay. Then this is called Y of B. All right. Then, if you remember from slope formula, right? It's just like y2 minus y1 over x2 over minus x1. If you remember that, so actually you it's similar like here. You are looking for the change in position, right? So from here, so from YB to YA, it was a distance, and you just take the YB minus YA to get the distance from YA and YB, right? So I'm gonna have YB, I take minus for YA, and then I divide it by the change in time, which is I take the B minus A. That's gonna tell me what is change in time over here, right? And that actually will give me the slope of the second line, a second line, right? About second line. Okay. Let me rewrite. Second line. All right. So now, what is a fact? If we let h equal to b minus a, right? It's h in here, so I'm gonna be this is a change in time, okay? Then b will be equal to a plus h. If you add h, sorry, if you add a both inside, okay. Then now you will have f. You will actually change this b over here to be a plus b, right? The input b now become a plus b, sorry, a plus h. And then you substitute this b minus a become h, right? And you're gonna have this form. What is that called? It's called the different quotient at a. And actually you can find the average velocities by this form. Okay, so let's do an example. Time is measured in seconds. A particle move a distance of yt equal to 3t squared meters. Find the average velocity between t equal to 1 and t equal to 1.1. Okay, so I have um, I I will have the average velocity gonna be um, if I use a formula, right? Velocity. I will now. I actually will use AV. Uh, Let me see. Uh, I'm gonna use AVR as average velocity. Or AV stand for average, and R is like a rate, right? Which is velocity, and then it's equal to y yb minus ya, right? If you remember the formula up there, divided by b minus a. So in here, what is that? You know that b was um, b was 1.1, right? And a is 1. I see that. Okay, so then you know that no, actually I'm gonna write a down here, right? So you see over here, like oh, I can use a T1 and T2, doesn't matter, right? But yeah, in in the form we learned above, actually, yeah, you can understand that if I rewrite it as like y of T2 minus y of T1 over T2 minus T1, something like that, then maybe you will not confuse with this. So T2 equals 1 and T1 equal to 1. Then now you can have y of T2 will be applied into the formula of yt here. You will have uh, 3 t squared now become 1.1, right? 1.1 squared, right? And if you use a calculator, you will have that's gonna be equal to 3.63. Okay. Okay. So and in another T1, you will have y of, maybe I change to here, become 1.1. Should be right, because T2 we know that's already. And for the T1, I have y1 will be equal to 3 times 1 square, right? We're equal to 3 easily. So now I can just substitute everything into this guy, this form, right? I have yt2 was 3.6. So average rate of change, our velocity will be 3.63 minus 3 divided by 1.1 minus 1. So then I'm gonna have use a calculator, you're gonna have 6.3 mile per second. Okay, so far so good. All right, let's have then another one question here. If average velocity in interval from A to B is slope of line L, then what should be the instantaneous velocity at time A. So let's move to this page. The, the definition of instantaneous velocity is limiting value of those average velocity over shorter and shorter time periods. So what does that mean? It's instead of like two point, like a bow problem, right? Now I try to make these 2 points become like go closer, closer, and closer, right? It's move closer and closer and become P only, become only 1 point. Like Q and P and it's kind of like so close and it could be like just 1 point, right? Okay, so that's called instantaneous velocity, um, and which is the limiting values of these average velocity over shorter and shorter time periods. Okay, so in that case, in the case before, we know that it's going to be the slope of the second line, right? The line that go through two distinct points. But the next case is instantaneous rate velocity is actually going to be the slope of the tangent line, right? The slope of the tangent line, which is P over here. So slope at this point of the tangent line go through this point, and okay, and then now let me see, and remember in this case it's called tangent line instead of secant line, because tangent line just touch only 1 point of the curve. Okay. So we done with section 2.1. I'm gonna go to 2.2. Let me see. Right.